This industrial drill costs $15,000. It takes 4 full hours to bore through just 30 centimeters of granite. 3,000 years ago, they drilled twice as fast, with copper tubes. Modern engineers still don't understand how. Welcome to Ancient Engineering. Today we're analyzing 5 tools that challenge everything we think we know about ancient technology. But this isn't an unsolved mystery. We're not going to talk about aliens or lost civilizations. We're going to show you the exact engineering principles they used and how to apply them today in your company, in your work, right now. Because by the end of this video, you'll know 3 manufacturing techniques that can reduce your operational costs by up to 60%. Subscribe, because what's coming you won't find in any modern manual. Tool number 1. Copper tubes that drill through granite like it's butter. Numbers first. In 2024, cutting 1 cubic meter of granite costs an average of $200. Industrial diamond bits last 50 hours. They cost between $300 and $500 each. Now imagine this. Cairo Museum, dusty display cases, and there, under dim lighting, physical evidence of something impossible. The Egyptians drilled granite 10 times faster than we do, with copper tubes. Copper, a metal so soft you can bend it with your hands. This isn't speculation, we have the evidence. At Giza, archaeologists found granite cores, perfect cylinders extracted from the rock, like when you use a circular cutter on dough, but on one of the hardest stones on the planet. Christopher Dunn, mechanical engineer, 30 years specializing in precision machining, he measured those cores with modern instruments. What he found is technically impossible by our current standards. The spiral marks on core number 7 reveal something extraordinary, a penetration rate of 2.5 millimeters per complete revolution of the tube. 2.5 millimeters per revolution. A modern drill equipped with industrial diamond bits penetrates 0.5 millimeters per revolution. Do the math. The Egyptians drilled 5 times faster than our best current technology. 5 times. So how? This is where simplicity beats complexity. The secret was never the copper. Copper is just the container, the structure, the delivery system. The secret was the system. Abrasion by suspension. Listen carefully, because this is applicable today. You take a hollow copper tube, 10 centimeters in diameter, 3 millimeters wall thickness. You prepare a mixture of finely pulverized quartz sand with water, exact proportion, 3 parts sand to 1 part water. You get a dense, almost viscous paste. You press the tube against the granite while rotating it. The paste gets trapped between the tube's edge and the stone surface. And here's the fundamental principle. It's not the copper that cuts. It never was. It's the microscopic quartz particles suspended in the paste. Quartz has a hardness of 7 on the Mohs scale. Granite, 6 to 7. Copper, barely 3. The quartz particles, driven by the pressure of the copper tube, literally pulverize the granite, atom by atom, grain by grain. The copper is just the delivery system, the vehicle, the conductor. The most extraordinary thing, we've replicated it. 2019, Cambridge University. A team built exact replicas of these tubes, same dimensions, same materials, same ancient technique. Result, 60% reduction in tool costs compared to modern industrial diamond bits. 60%. Now the numbers you can present to your boss tomorrow morning. Industrial diamond bit, $500 per unit. Lifespan, 50 hours of continuous operation. Copper tube system with abrasives, $50 per unit. Lifespan, 200 hours, 200 hours of work. Diamond bits, $2,000 in tools. Egyptian system, $50. You save $1,800 every 200 hours of operation, and this isn't laboratory theory. Restoration companies in Italy are using it right now for precision work on historic marble. The formula: religiously maintain the 3-to-1 ratio, quartz sand, water, constant pressure. But that is just the beginning. Tool number 2. Granite jars with tolerances that would make a quality control engineer weep. A state-of-the-art CNC mill, the kind Boeing and Airbus use for critical aerospace components. Cost, $500,000. That machine achieves tolerances of 0.01 millimeters working metal. Extreme precision, cutting-edge technology, the best humanity can manufacture today. Egyptian Museum in Cairo, pre-dynastic artifacts hall, 5,000 years old. Granite jars, measured tolerance 0.002 millimeters, 5 times more precise than our most advanced CNC technology. When I first heard this, my immediate reaction was, impossible. Measurement error. It has to be an error. So I went straight to the data. Ben Van Kerkwyk, engineer specializing in precision metrology. He scanned 12 jars using an $80,000 laser scanner, the same equipment used to inspect jet engine turbine blades. The results are disturbing. Internal walls, perfectly symmetrical. Wall thickness variation less than 20 microns across the entire circumference. 20 microns, 0.02 millimeters. For context, a human hair measures between 50 and 100 microns thick. These jars have variations smaller than half a human hair, carved in granite, one of the hardest and most brittle stones in existence. Here's what's truly disturbing. 2016, University of Manchester. A team accepts the challenge. Replicate a single jar using any available modern technology. No budget limit, no time limit. 340 hours later, $12,000 spent. Total failure. They couldn't match the precision. So how did they achieve it 5 millennia ago? Denis Stocks, experimental archaeologist, 20 years dedicated exclusively to answering this question. And he found the answer. It wasn't a magic machine. It wasn't alien technology. It was something far more sophisticated than any machine. A process. Continuous iterative calibration. It works like this. Bow-powered lathe. Speed 4,000 revolutions per minute. We'll get to that in a moment. Cutting tool. Dolerite stone soaked in emery paste. Emery, natural abrasive, hardness 8 on the Mohs scale. But the real secret isn't the tool, it's the measurement system. Cedar wood templates, hand-carved as exact replicas of the desired internal profile. The process. Work 2 minutes. Stop. Insert template. Verify exactly where excess material remains. Remove only that material. Verify again. Repeat 100 times, 200 times, 1,000 times if necessary. Measure 100 times. Cut once. That was the secret, not the machine, the process, and this has massive consequences for contemporary manufacturing. A Swiss aerospace company studied this Egyptian technique. They asked themselves, what if we apply continuous verification instead of final inspection? They implemented checkpoints every 3 minutes throughout their entire production line. Measured result, 23% reduction in defective parts, 23% less waste, just by verifying more frequently. See the pattern emerging. We spend millions on increasingly sophisticated machines, but we neglect the fundamentals: process, verification, control. The Egyptians understood something we've forgotten. Precision doesn't come from the machine, it comes from the process. And speaking of processes that defy all modern logic, tool number 3. 3-meter copper saws, cutting granite like it's softwood. The quarries, where empires are born. A modern diamond cable saw cuts 5 cubic meters of granite per day. The cable, impregnated with industrial synthetic diamonds, costs $20,000. Durability, 6 months of intensive use. Now travel with me to Aswan, southern Egypt, the most legendary red granite quarries in the ancient world. Here they extracted blocks for 100-ton obelisks, colossal statues, imperial sarcophagi, and throughout the quarry, carved directly into the bedrock, we find physical evidence of giant saws, 3 meters in length, cutting 50-ton blocks. The marks in the stone tell the complete story. James Harrell, petrologist from the University of Toledo, world expert in structural rock analysis, years studying 43 different blocks from these quarries. The marks reveal a perfectly consistent pattern, nothing random, everything systematic. Parallel cuts spaced exactly 2.5 centimeters apart. Uniform depth, 6 millimeters per complete pass. Perfectly straight striations along meters of continuous cutting. Harold calculated the speed based on the pattern of marks, approximately 15 square centimeters per hour for a 2 meter by 1 meter block, 130 hours of work. Today, without industrial diamonds, that same block with hammer and chisel, you'd never finish it. Literally, you could die trying. Deny stocks again. 2001. He built a functional replica of an Egyptian copper saw. It worked. Same principle as the drilling tubes, distributed abrasion under pressure. The copper blade, 3 millimeters thick, 3 meters long, looks fragile, looks like it would break just by looking at it. But the trick is simple. The blade doesn't cut anything. The blade only transports the abrasive. The mixture, pulverized quartz, water, gum arabic. Gum arabic is natural resin that makes the paste adhere better to metal during movement. Tension applied via counterweights, exactly 80 kilograms. This keeps the blade perfectly straight and stable during hours of work. 4 people, 2 on each side. Rhythmic, constant back and forth motion, like you're sawing wood, but at monumental scale. Every 15 minutes, pause, apply fresh abrasive paste. Continue. Stocks cut 10 centimeters of Aswan red granite in 7 hours of work. 10 centimeters, the exact same stone the temple builders used. 7 hours. And here comes the application that will interest every aerospace engineer listening to this. This principle of controlled distribution of abrasive under constant tension has a revolutionary application in modern manufacturing. Sandvik AB, Swedish multinational, global leader in precision industrial tools, they developed an abrasive cable cutting system specifically for carbon fiber. Why does it matter? Carbon fiber is extremely heat sensitive. Generate too much heat during cutting, and you destroy the material's molecular structure. It weakens, becomes useless. You lose the entire piece. The system, inspired by the Egyptian principle, cuts completely cold, zero heat generation. Direct economic comparison. Diamond saw for carbon fiber, $20,000 initial investment. High heat generation, requires complex cooling systems, constant maintenance. Abrasive system, based on ancient Egyptian technique, $2,000 initial investment. Cold cutting, no additional cooling needed, minimal maintenance, 90% reduction in initial cost, and the resulting cut is superior, cleaner, more precise edges. Zero structural thermal damage, 4,000-year-old technology, solving 21st century engineering problems. Tool number 4. Bow drills spinning at 4,000 revolutions per minute. No motor, no electricity, no fuel. This is going to change your understanding of basic mechanics. A professional Bosch or DeWalt electric drill, high-end, the kind used in industrial construction. Speed 3,000 revolutions per minute, consumption 750 watts of continuous electrical power. The Egyptians reached 4,000 revolutions per minute using only a wooden bow and linen cord. The first time I saw this depicted in ancient murals, I thought it was symbolic, decorative, stylized art. It couldn't be functional. Deny stocks. Again, 20 years testing, failing, adjusting, refining this specific tool. He succeeded. With an 80-centimeter bow and the correct technique, he drilled 6 centimeters of quartzite in 3 hours. Quartzite, harder than granite, with a stick, natural fiber cord and a copper tube. Now the physics behind this, because this is engineering in its purest and most elegant form. The bow drill works through simple but brilliant mechanical multiplication. The bow measures 80 centimeters long. When you move it side to side, the cord wrapped around the vertical spindle makes it spin at high speed. Here's the mathematical magic. The spindle has only 2 centimeters radius, circumference, approximately 12.5 centimeters. For every 80 centimeters the bow travels, the spindle completes approximately 6 full revolutions. Multiplication ratio 40:1. If you move the bow twice per second in back and forth motion, the spindle rotates 12 times per second. That's 720 revolutions per minute per bow pass. but the movement is bidirectional. You cut in both directions, so in practice, with an experienced operator maintaining constant rhythm, sustained average, 4,000 revolutions per minute, 4,000 RPM, no motor, no electricity, no fossil fuel, no batteries, just physics, geometry, practice. Now you might think academically fascinating, but who would use a bow drill in 2024? Let me tell you about an organization working in Tanzania, rural areas, no access to electrical grid, communities desperately needing to drill drinking water wells, water that literally saves lives. An electric drill for well drilling, $1,500, plus diesel generator, plus constant fuel, plus specialized technical maintenance, total cost prohibitive. This organization adapted the Egyptian bow drill design using completely local materials. Total cost $15, no electricity, no fuel, no dependence on international supply chains. Since 2018, they've drilled 1,200 functional wells using exclusively this ancient technique. Average savings per community, $1,200. But more important than money, access to drinking water, reduction of waterborne diseases, survival, 4,000-year-old technology saving lives in 2024. See the pattern emerging clearly now. The most complex solution isn't always the best solution. Sometimes the simple is the brilliant. Tool number 5, water levels achieving 0.5 millimeter precision across 100 meters. No laser, no electronics, no digital calibration. This is my favorite, because it perfectly represents the complete philosophy of Egyptian engineering. A professional construction rotary laser level, the kind used for 50-story skyscrapers. Cost $3,000. Specified precision, plus or minus 1.5 millimeters at 100 meters distance. Advanced laser technology, photodetectors, real-time digital processing, automatic calibration, incredibly sophisticated. The Great Pyramid of Khufu, 230 meters per side. Total perimeter, 920 meters. Level difference across the entire complete base, less than 2 centimeters. Let's do the calculation together. 920 meters of perimeter. Maximum unevenness, 2 centimeters. Relative precision, 0.002%. 2 centimeters in 920 meters. That exceeds our most advanced laser levels. 4,500 years ago. No electronics, no lasers, no computers, no GPS. How? Mark Lenner, American archaeologist, complete decades studying exclusively the Giza Plateau, not an armchair theorist. He's a man who excavates under the sun, who measures, who meticulously documents. Lenner discovered something extraordinary. Channels carved directly into the bedrock, channels that completely surround the area where the pyramid was built. These channels weren't decorative, they were pure functional engineering. Massive-scale hydraulic leveling system. The system works with the most fundamental principle of physics, communicating vessels. Water always seeks its own level, always, without exceptions. Container shape doesn't matter. Horizontal distance doesn't matter. If you connect 2 points with a water-filled conduit, the level will be exactly identical at both points. Gravity, fundamental physics, immutable law of nature, the Egyptian process. They carved a complete perimeter channel in the bedrock. Depth, 10 centimeters, meticulously following the entire construction area contour. They filled the channel with water until reaching a constant, stable level. They placed permanent reference marks every 5 meters along the entire channel. These marks touched precisely the water surface. System precision, limited only by water's surface tension, approximately 0.5 millimeters, 0.5 millimeter of precision, with water, with rock, with direct visual observation, nothing more. And this isn't just fascinating ancient history. A contractor in India read about this technique in 2022. Project foundation for a 20-story residential building. Irregular, mountainous terrain with multiple visual obstructions. Using laser levels was extremely complicated due to topography and distances involved. He decided to try the ancient Egyptian system. Cost of the rotary laser level he had planned to buy, $3,500. Cost of the hydraulic system, $80. Industrial-grade transparent hose. Non-toxic vegetable dye for visibility. Simple wooden supports. Precision achieved plus or minus 2 millimeters across 150 meters of irregular terrain. 98% reduction in equipment cost, with absolutely comparable precision for the project's required standards. If you work in construction, especially large projects on complicated terrain, listen to this carefully. Transparent hose, internal diameter 15 millimeters, length whatever you need for your specific project. Completely clean water. Add vegetable dye to improve visibility under different lighting conditions. Wooden supports every 10 meters to maintain hose stability and avoid sags that generate errors. Crucial, cross-verification. Never trust a single measurement. Verify from multiple independent points. Triangulate your measurements. Construction companies in Bangladesh, Nigeria, Peru are implementing this right now. Documented average reduction, 40% in complete foundation phase costs, 40% savings, using physics known 4 millennia ago. And with that, we reach the end of our 5 tools. Let's review what we just saw. 5 tools that completely challenge our understanding of ancient technology. Copper tubes drilling faster than modern industrial diamond bits. Stone jars with tolerances exceeding $500,000 CNC machines. Saws that cut without generating heat, perfect for sensitive materials. Drills reaching 4,000 RPM without consuming a single watt of electricity. Levels achieving sub-millimeter precision using only water. But the real lesson of this video isn't that the Egyptians were technologically superior to us. It's not that they possessed secret knowledge or supernatural help. The real lesson is much deeper and more applicable. We have forgotten fundamental principles. We've confused complexity with intelligence. We've confused technology with engineering. We've forgotten that the best solutions are often the simplest. If you're an engineer, architect, builder, manufacturer, listen to this with absolute attention. These 5 techniques can reduce your operational costs between 40 and 60% in specific areas. 1. Abrasion by suspension. Cutting hard materials without expensive industrial diamonds. Documented savings, 60% in tool costs. 2. Continuous iterative calibration. Achieving extreme precision without million-dollar CNC machinery. Proven reduction, 23% in defective parts and waste. 3. Distributed tension with abrasives. Completely cold cutting, ideal for thermally sensitive materials. Savings, 90% in initial equipment cost. 4. Simple mechanical multiplication. Generating rotational power without electric motors. Applicable in remote areas without infrastructure. Cost 98% lower than motorized alternatives. 5. Hydraulic leveling by communicating vessels. Millimetric precision without laser equipment. Reduction, 40% in foundation phase costs. Next time you observe ancient technology, don't simply ask, how did they do it? Ask something much more important. Why did we stop doing it this way? Because many times, the most intelligent solution is also the simplest. If this video changed your understanding of engineering, if it made you reconsider the relationship between complexity and efficiency, do 2 things immediately. First, subscribe to Ancient Engineering. Every week we analyze techniques your competition completely ignores, techniques you can implement tomorrow in your operation. Second, share this video with an engineer, architect or builder you know, someone who would directly benefit from this applicable knowledge. And if you think what you just saw was impressive, wait for the next episode. We're going to analyze Roman concrete, that material that's been submerged under salt water for 2,000 years and is getting stronger with each passing century. While our modern concrete disintegrates and crumbles in barely 50 years, what did Roman engineers understand that we've completely forgotten? We'll discover it together next week. Thanks for your time, thanks for your attention, and always remember, the best technology isn't always the newest. Sometimes it's the oldest. See you in the next episode of Ancient Engineering.